Hello, my name is Matthew Krupsak, and I am the founder and president of Theta Informatics LLC. And this video is a demonstration of a new system that we've developed for object tracking and Kalman filtering to be used with OpenAthena Core on live drone video feed. So essentially what our company's OpenAthena Core software does is it implements a novel terrain-raycast technique that removes the need for a laser rangefinder on most drone platforms for uh, ranging and geolocating ground objects of interest. So basically, the OpenAthena Core software is able to do something called a terrain raycast, which basically simulates the effect of a laser rangefinder, but in software rather than hardware. So given a drone camera's position, orientation, and pixel of interest, OpenAthena Core is able to do a terrain raycast to basically detect the range and then geolocate anything that a drone camera can see. So that method in itself, for any pixel of a given image frame, we might see between 8 to 12 meters is kind of typical because of some error in mainly the orientation of that drone camera's gimbal. So what we've developed here with this new tool is a system that implements Kalman filtering and tracking to basically refine location estimation the longer a given object is observed by a drone camera. So here on the top left of the screen, we can see there is a object detection model running live that is doing detection with a neural network of common objects, say like a person or a car, a bike, boat, etc. And then basically this model is predicting a bounding box and a confidence score for that type of object. What we see here on the top right is a visualization in the Android Team Awareness Kit software, or ATAK, published by the Department of Defense and TAC Product Center under the United States government. So TAC is essentially like a shared Google Maps type of interface. It was originally created for the Department of Defense and the military, but now it is increasingly being used for dual use situations as well, such as law enforcement, public safety, search and rescue, and more. On the bottom right here, we see the output of our track tool that we've developed that's doing that consistent object tracking and filtering using the terrain raycast results obtained from OpenAthena Core. So basically, um, what the script is doing is every frame it's getting that bounding box and the center of it. It's uh, pulling telemetry data with the drone camera's position and orientation, and it's combining those into a calculation request that's sent to OpenAthena Core, saying, hey, for this camera position, orientation of pixel of interest, what is the range and ground location of the thing that I'm looking at? Within a couple of milliseconds, OpenAthena Core is returning that result, which basically tells it the latitude, longitude, elevation, and then predicted circular error of that given object. So for any one pixel in any one frame, we might have 8 to 12 meters of error. This Kalman filtering implementation is essentially refining that to a more accurate location estimate the longer a object is observed. This implementation that we've built is also doing some other fancy stuff like Hungarian algorithm bipartite matching to correlate um, objects from one frame to the next so that we can get consistent object tracks for many different objects in each video frame without duplication or missing objects. So I'm just going to kind of show what the typical performance here might look like. Now for this example, we're using simulated drone camera position and orientation up a few dozen meters off the ground and pointing it at a 45-degree angle. In an actual deployed use case, these Object detection boxes would, of course, be a lot smaller as we're looking at pedestrians, vehicles, etc., from a overhead and potentially non like straight up and down view. So any kind of like slew of the camera, basically. So as the object is moving around per frame, that tracker is updating its position, uncertainty, and velocity estimate as it's observing that object move. And then when the object disappears from frame, its status is changed from confirmed to coasting. So even if the camera doesn't see it, it's anticipating that the object still exists, and it'll essentially project its last known location and velocity for a few seconds until it treats the object as lost. And then when a new object becomes present within the video frame, it's starting to track it here as a new object, as we can see in the visualization on the right. Now, the nice part about this implementation and how it's doing that tracking and gating between tracks is it's actually smart enough to see if an object temporarily comes out of view and then is reacquired, it's still able to correlate that as the same object. So unless its velocity or position is much different than we expect past a certain threshold, it'll be able to reacquire that object. Oh, okay, in this instance, it apparently didn't because I moved too quickly. But we can see there in that example that it reacquired me and was tracking it consistently. So these parameters need a lot of tuning. We've kind of tuned them here for this bench setup. But if this was an actual overhead drone camera looking at people, that would have been a very rapid acceleration and velocity change. So these are all kind of configurable, but that just gives you an idea of what's going on behind the scenes. So essentially, objects will transition through several states after they're seen in a certain number of video frames consecutively or within a limited window. The object track goes from tentative to confirmed status, after which it will start populating to ATAC using the cursor on target protocol. When that track disappears from the video frame, its status is changed to coasting, where basically the Kalman filter is basically predicting its location based on last known location, velocity, and uncertainty value. And then after a number of seconds, by default, we've set it to about 8 seconds. When an object has not been updated, it's treated as lost. And we can see up there on the visualization that they'll start to gray out and then disappear from the map shortly thereafter, so that we're not cluttering the common operating picture with a bunch of old data.